It's the first time. It's already included in the conference fee, and it costs 80 reais and includes the meals and wine and juice and water. Um, and it's a nice place, so see you there later. And for those that have to pay, please go as soon as possible to pay beer or Stephanie.
Okay, so next speaker is Tobias Fritz, and he talk about joint work with Theorem, Las Cuevas, and
Tim?
okay,
Yeah, thanks. Do I have the time now somewhere? Just, or maybe I can look at the laptop here.
yeah, okay. But I can tell you.
Okay. Yeah, thanks. Yeah. Cool. Okay. All right. So I want to continue the theme of hierarchies of semi-definite programs. And in some sense, in a very simple setting. And so this is an approach to a problem where I'd be curious to know if somebody else has other potential applications for this. So the problem that we're addressing is if you're given a bunch of moments, m to the trace of m to the k, so this is always going to denote normalized trace. So of some Hermitian matrix, so for k from 1 to n, let's say, of some Hermitian matrix M, could in principle also be an operator in some sort of Neumann algebra or something. Then, and I want to assume that the infinity norm is less than or equal 1. But this is, we can in principle also do without this, but this helps. Then what can we say about whether M is positive semi-definite or not? Well, I'm sure that many of you already know the answer to this and how to do this. But now a little bit more quantitatively, we might want to ask, well, if this is not the case, then what can we say about how far away M is from being positive semi-definite? And so this is more like the actual problem, the more interesting problem that I'd like to consider. So what can we say about the distance to the positive semi-definite cone in the LP norm, LP Schatten? So P could be 1, in which case we're talking about a trace distance. So the LP distance, and I'm going to denote this by d sub p of m, defined as the infimum over all positive semi-definite matrices P. P. Okay, sorry, this is now a little p and an uppercase P. Yeah, so this is the quantity that we want to sort of compute. And let me just give a little bit of motivation how we came up with this. Was in an application that Gemma de las Cuevas is working with, which is matrix product operators. And so there you have matrices that, now I'm slightly simplifying this, but they're maybe of the form as follows. You have a very large number of tensor factors. And then you may have a thing like this. And the number of tensor factors may be so large that you cannot even write down this M in an orthonormal basis. You just cannot, for example, on a computer. It just there wouldn't be enough memory to even store all the entries of M, let alone do some sort of Cholesky factorization or diagonalization or computing determinants or whatever. So that means we need to do something in order to decide or get at least some information about how far away M is going to be from being positive semi-definite. We need to do something more indirect. And so what we can at least try and do is to say, okay, well, given these local matrices AI, we can at least, for example, compute a trace of M. We can look at M squared, and we will have a similar form to this, just with a double sum. We can compute a trace of that, and so then we can compute a trace of M cubed, and so it's just generally a bunch of moments like this. And so this is sort of the thing that we have access to, while the M as an entire matrix is just way too large. Okay, another potential application which we haven't really thought about yet is the case of sparse matrices, potentially. There we might have the same situation. When you have a sparse Hermitian matrix, also it may be hard to, I'm not really sure about this one, but at least one can imagine that it's easy to compute the moments, and maybe it's difficult to determine whether M itself is positive semi-definite or not. Yeah? Well, theoretically, yes. I'm going to get to that next, but in practice, well, you can't diagonalize, right? Yeah. Oh yeah, I'll get to that. Yes. Yeah, that's right. Certainly not so surprising. It takes a bit of matrix analysis. Okay. Anyway, so yeah, as you're kind of already hinting at, the answers to these questions obviously are, well, invariant under conjugation by unitaries. So in particular, they only depend on the spectrum. And a good way to think about this, relating back to the things that we've already heard about, is to actually phrase this in terms of the spectral measure. So equivalently, they only depend on the spectral measure, by which I mean the measure on the real line that is just given by, you take a point mass at each eigenvalue, and then you normalize to a probability measure. So 1 over d reduced to dimension. So this is a probability measure on the real line. And basically, so the moments of M are not just going to be the moments of this measure. It's just a straightforward computation. And then we're basically asking, is this measure concentrated on the positive half-line? Or is it supported on the positive half-line, or are there negative values in there? And how far away is it? So let me just write down this general problem. Now we can do this for a general measure. And so then we got, in our setting, the Hausdorff, a version of the Hausdorff moment problem. So more generally, given moments, so moment is an expectation value of the function x with a k. Of some measure mu, some probability measure mu. What can we say about, well, in this case, the LP distance, so this in the setting of probability measures, this distance turns out to coincide, or is called the LP Wasserstein distance. What can we say? So some of you may have heard this name before in the context of optimal transportation. And so this is exactly what it is. How much do we sort of have to pay in order to take these negative eigenvalues or these negative, the mass that's on the negative half-line and transport it to the positive half-line. So certain costs associated to that. And in the case of a spectral measure, that distance turns out to coincide exactly with that LP shot norm distance. So here we're looking at the distance to the measures on set of measures supported on the unit interval. Okay, so secretly this is the problem that we're addressing. But just to keep things simple, to keep the notation simple, I'll just, and maybe more familiar to you, I'll keep using matrix notation. And to talk about traces of powers of the matrix M. Okay, so, sorry. And now answering the question that was already asked, in the matrix case, or also, well, in the case of these measures, the question is, well, how do we actually, is there a minimizer here, and what is the minimizer? And I guess there's an obvious guess, and that turns out to be correct. So the closest point in the PSD cone is you just take the positive part of M. So you take, if you want, you can diagonalize it, and you just set all the negative eigenvalues to 0. So the closest point in the PSD cone is M plus, so the positive part. And this leads to a formula for this distance, which we're going to use in the following, and given by, well, if you subtract the positive part from M, what remains is the negative part. So this means just the negative eigenvalue, you throw away all the positive eigenvalues, replace them by 0, and you take the absolute value of the negative ones. So this is the negative part, and we're interested in the P norm of that. Okay, at this point I should maybe say a little bit about related literature. So as far as I know, maybe the first to kind of maybe implicitly address this sort of issue is in a paper of Jean. Yeah. What was von Neumann's trace theorem again? Okay, that's not how. Maybe it's possible to use that. I don't know, but we've used one of these standard matrix analysis inequalities, where that A minus B for any, I guess, unitarily invariant norm. This is greater than or equal to the distance in, if you diagonalize and order the eigenvalues, this sort of thing. This is what it's based on. Okay, so using the semi-infinite hierarchy, there's a pretty simple and an elegant way to compute this for the infinity norm. In which case we're basically asking, well, can we lower bound the support of the spectrum of M? What is the smallest eigenvalue? Yeah, so then in the context of quantum information, there was a paper by Hilary Carteret from something like 2 years ago. Her goal was somehow to bound the entanglement negativity, which is something I don't know anything about. But this was in the setting, so for p equals 1. Also, I think her methods are general. And this is closely related to what we've done. But her methods then involve computing determinants and finding roots of polynomials. So I think this is numerically going to be a little bit problematic. Numerically kind of unstable. So yeah, probably. Oops. Okay, so our goal is to compute that. And so let me introduce a piece of notation. Namely, related to that, taking that negative part. So let me write fp of x for the function that is 0 on the positive axis, and that is given by x to the p or on the negative axis. So for p equals 2, just to illustrate, I'm going to use this plot in the following. It looks something like this. Okay. So then what we're interested in is really dpm by that lemma. So the p norm of the negative part, well, the negative part is already positive semi-definite, so we might as well just take the pth power and take the trace. So this means that we're really interested in this quantity. Okay, so this is what we try to compute. And now, of course, because we don't have explicit access to m, we can't compute it exactly, so we can only find bounds, because we're only given the first n moments. Pretty much, yeah. So the obvious thing, yeah. So yeah, I guess I can't claim that any of this is really very rich. Okay, so now let me write dpn plus for the optimal upper bound. So this means the supremum of that quantity, so sort of the worst case scenario of that distance over all m prime which have the same moments as m. Same, I mean first n moments. And likewise, dpn minus corresponding infimum as above. And so there's a bit of a subtlety here. Which are the m primes that you optimize? Do we optimize only over matrices of the same size? In which case, these are really hard problems, and I don't know how to go about them. Or do we allow the m prime to be of different size? Meaning, basically, in the language of these measures, do we allow arbitrary measures in this optimization? Or do we restrict to this, finitely supported uniform measures on a real line? And so the latter is what we do, and then indeed and in this sense, with this optimization over these m primes, these are the quantities that we're going to compute. These things, this is what we can compute. What's the time? Okay. 28? Okay, thanks. Okay, so this is as was already mentioned, we can try to so what we can do is also we cannot really, from just knowing the first n moments, compute sort of the expectation value of this function. What we can do, though, is to compute the expectation value of any polynomial of degree at most n. Right? Because so if we know the first n moments, then we know the expectation value of any x to the k for k less than or equal n. And then by linearity, we also know the expectation value of all these polynomials. So at least what we can try to do in order to get bounds is to upper bound and lower bound this function by polynomials of degree at most n. And so then what we've shown is indeed that when you do this, then you get these essentially optimal bounds. And yeah, this is again also not too difficult, but it's just involving a very simple application of the Hahn-Banach theorem, basically. So in order to compute the upper bound in the distance, right, so if you want to upper bound this quantity, we better use polynomials that are above this function. So, and then we try to minimize that. So I'm going to use optimize over all polynomials q of degree at most n that are above that fp. And then take the expectation value of that q. And likewise for the lower bound, I'm going to use lower approximations. And then try to maximize the value. So the only maybe not so obvious thing is what do we do with these inequalities? How do we get a handle on saying that q is greater or equal fp? But that's also not too hard. Oops. Okay. So it means we need to understand what these inequalities mean on a polynomials bounding function. And so here, the again pretty simple observation is that fp, although not a polynomial, is a piecewise polynomial. So this means that what we want, so it is equivalent to looking at the individual pieces. Well, so let's just look at the positive axis. So I had assumed an upper bound on a spectrum of 1, so this is why here I only have the unit interval. And now then for the negative part, I want this, basically want this absolute value of x to the p on the right hand side here. And so now if I take x to be non-negative, this means I want q of minus x to be greater than or equal x to the p, again for all x in the unit interval. And now these are nice inequalities, because what we have here on all four sides of these two inequalities is just, well, polynomials. And we want to have an inequality of polynomials on the unit interval, and this is something that we understand very well. So the point now is positivity, or non-negativity is really of polynomials on the unit interval is well understood. Yep. Oh, sorry. Yes, thanks. I forgot to say that. Yeah. So in order for that to make sense, we need for this to be a polynomial. P should be an integer. I guess 1 and 2 are the most interesting cases. Or maybe large P in order to get some bounds on the infinity norm. Okay, so what we use is this sort of positive Stellensatz type statement that a polynomial, and so these things are particularly simple in the one-dimensional case that we're in. So a polynomial q of degree less than or equal to m. So here I just want to have an even number, so I'm sort of changing the index here. Is greater than or equal to 0 on no, I realized that in my notes I have r plus instead of unit interval, so I hope I'm actually getting this right. Please correct me if and only if. Yeah, right. No, so we've seen this earlier. Essentially, the Poutinar's positive Stellensatz, but now in this one-dimensional case, we don't need strict positivity. For positive semi-definite matrices A, B, C. Okay, so these are matrices of size m by m, and here we just have the vector of monomials acted on by these, and here we're just taking these inner products. And so this means optimizing over this Q. Well, no, this is an SDP, right? So oh, and by the way, this is in this one-dimensional case also pretty easy to show if you just use, the fundamental theorem of algebra. So you write Q as in terms of simple factors involving real roots, and then a complex roots that give degree 2 factors. And then you basically more or less just get this by staring at it a little. So optimizing over Q, non-zero, Q greater than or equal to 0 on the unit interval, is an SDP. Okay, so this means if we take all this stuff together, that we can solve this problem. So doing this, computing this infimum, so this is actually an SDP. Right? Because so we introduce some variables for the coefficients of Q, and then we need to impose this inequality, and this inequality decomposes into these two parts, and for each part we just introduce these unknown semi-definite matrices over which we need to optimize as well, and so this is how we get an SDP. And likewise for the lower bound. Okay. Yeah, but what somehow I find remarkable is that the original problem was somehow having to do with positive semi-definiteness, and now we're reducing it again to a problem involving semi-definiteness, and somehow it seems to bite its tail. And I wonder if that's, maybe if anyone knows about this Shor-Horn problem where something similar seems to come up, I'd actually like to learn about that. Okay, yeah? Oh, yes, right. So, thanks. I guess I had gotten something. No, I think this is still correct. Just that somehow you. Okay, no, I realized I wasn't very careful when writing my notes, but so. Yes, thanks. Right. So you can write it and as a sort of. So maybe I should better write it like this, as a sum of squares decomposition with so where each sigma I is the sum of squares plus such that the overall degree or the degree of each summand is at most this 2m, right? Yes, yeah. So we've done that as well. Yeah. It gives a bit of a smaller SDP, but doesn't quite achieve these values. But yeah, that may be better in practice because it's smaller. Okay, so such that the degree of each term. Well, yeah, I'm not going to write this down anymore. I wanted to write down a form like that just in order to make it more clear it's actually an SDP. Yeah, interesting question. I don't know. Maybe it's when there's just the measure is supported and just two extreme atoms, but I'm not sure. So it was okay. So for large n, solving these SDPs may still be difficult. And so we've also looked at linear relaxation, which also Jean was in a way talking about this morning, or at least a close variant. Based on another representation of positive polynomials on an interval. So the Handelman decomposition. So if we have a polynomial that is strictly positive, on the unit interval, then we can write it in the form there's a sort of list, double indexed list of coefficients, and now it's just these. So a polynomial like this is obviously non-negative on a unit interval, and if you take a bunch of positive linear combinations of polynomials like this, it's still non-negative. Yeah. Yes. Yeah. So it only So they actually only enter via the objective function. So the objective function is this. We're optimizing this Q. All the constraints are independent of M and independent of the moments, but they enter here as in the objective function because, we evaluate any polynomial of degree at most n on the matrix using this expectation value by expanding via the moments. So if Q is like this, then this is sum over k, qk, trace of m to the k, right? Okay, so for this linear relaxation, we use this Handelman decomposition, where now these are all non-negative. So what we can do is to relax the condition I have the conditions that this is non-negative on 0, 1 and q minus x going to equal x to the p, while both on the unit interval. 2 saying that there should be a decomposition like this, but where we bound these exponents by a certain number we choose in advance, and we've sort of arbitrarily, at least in our implementation, we've also made these put the bounds such that alpha plus beta is exactly also equal to the degree of the polynomials that are equal to our n, which is the largest moment that we assume. But that is perhaps a bit of an arbitrary choice. So yeah, we relax this to q equals alpha beta with alpha plus beta less than or equal n. Now the point is that by Handelman's theorem, if this has degree n, then you can always write it in this form. But in general, you need to go higher in alpha plus beta than n. So for example, I think Jean also likes this example. If you take something like x minus 1/2 squared, then it's not so hard to see that it will not be able to write it in this. Oh, sorry, this is not even strictly positive, but yeah, these are sort of difficult examples. So this is really a proper relaxation of the problem. Well, it's a relaxation of that in the sense that we got a worse bound. That's, yes, thanks, right. Yeah, good point. Okay, and so for the other equation, we take make the same, simply the same ansatz. And so now, yeah, we have this is now a linear program, right? Because now we don't have any sort of positive semi-definite matrices anymore, any sort of constraints like that. Only that these coefficients need to be non-negative, and otherwise the coefficients of Q are also unknown, but kind of determined by this. Okay, yeah, so this is basically more or less all that I have to say. So this, although Jean was, I think, saying earlier also that in general these types of linear relaxations are not so useful, at least in this one-dimensional case. For us, this seems to work pretty well. In general, you have to go to higher moments in order to witness a little bit of higher moments in order to witness the non-positive semi-definiteness, but it's a lot faster. Yeah. So this seems to work well in practice. The SDP method also. And yeah, in case that anyone would be interested in also using this sort of thing or has problems of this type, yeah, please let me know and I can provide our implementation, the code that we have so far. It's probably not of great quality and very user-friendly, but yeah. Would be good to get some feedback in case that somebody wants to try it out. Okay, thanks. Oh, and if anyone knows of sort of, let's say, more prior literature or something, I mean, I feel like this whole stuff is not too original. I'd also be interested in hearing about it. Is what? Oh. Yes, we can also do, so we haven't looked into this